Hello, everyone. Good evening. We will start with the session. Let me share my screen. Yeah. So, like this session is very useful. If I'm going to start this because whatever which we are going to learn today will be like mostly aligned to whatever which we are going to do in terms of ChatGPT. Okay. So we today we are going to discuss more about how did a sequential model got evolved and conformed, and kind of co-founded as transformers, and how this transformer evolved as large language model, and how this large language model evolved as ChatGPT. So we'll be like understanding the entire history behind how does this entire things have happened in the past years, and how do we understand it better. It's always an important thing, because without understanding how ChatGPT architecture works, you might not know the right prompts, or you might not know like what is the aesthetics behind it. So let's get started with it. So let's say usually whatever networks which we have saw in the previous days, it is all about normal feed forward neural network. But that is like it can able to handle the current data, correct? Let's say a current data in the sense like you will be giving a set of data, and that data will be given as an input. For that particular input, it will give you an output. Let's say an image. You give an image, you say an output. Let's say an object is present, or some disease is present, or something like that, correct? And even though when we did this PIMA Indian diabetes data set, right? So we did have some 8 columns of data, correct? And with that 8 columns of data, we did push that data for the classification. The classification said either it is 0 or 1. It doesn't require any previous state inputs, correct? So that's the essence of a normal feed forward neural network. Yeah, but before I go into this recurrent neural network, there's one more point to say here. If you have any doubts or clarification regarding like downloading the materials or the course and everything, the last 10 minutes, the respective people will be like get in touch with you. You can clarify those doubts with them. Okay, just send it up. So you'll be getting if you have any queries in the material handling or accessing the material and stuff, so you can very well contact the fag end of the session. That's the last 10 minutes. Okay, so now coming back to the session, as I told you, yes, whatever data which we have handled, it is totally onto a current state. But when it comes to musics or some let's say some conversations, it is totally depend onto the entire conversation. Let's take an example. I will say like I am a good boy. Okay, so what if I say just I am? Okay, or what if I just say good boy? Can you create an ideology behind what does this good boy means? Because good boy can be anything. It can be a brand, or it can be you might be complimenting someone, but you don't know which one, unless and until you know the previous state inputs. The previous state input is saying I am a good boy, or Ravi is a good boy, so which means that I'm stating towards Ravi, which means that obviously I cannot give the entire state data as an input to the network, because if I give it like that, the model will never understand the aesthetics behind it. So that's where a sequential handling is required. Okay, so that is where this recurrent neural network comes into play. Okay, because it can able to handle sequential of data. For example, even in Google search, when you do this, for example, who is Barack Obama? Just try that thing. You can just type who is Barack Obama, and the next search you can just say his wife name. You don't even want to mention Barack Obama's wife name. You don't want to even mention that, because since your first Google search is on Barack Obama, if you just type his wife name, it will give you relevant result, because it is able to handle the previous content as well. That is the importance of processing a text. So that's what we call as natural language processing. So whatever we have discussed yesterday, right? So natural language processing is not that easy. A single smiley can create a different meaningful insights. So in that way, we are requiring a model that can able to handle sequential data and it can able to memorize the previous contents within it. Okay, it should not be focusing only onto the current statement, but it has to focus on the previous statement also. So that is very, very important. Yeah, sorry. That is very, very important for a particular neural network. Okay, so which means that if you are having a recurrent neural network, this kind of problem can be solved. That is, if I, okay, maybe like what I will do is I'll just type some, okay, give me a second. Okay, so I'm going to type a content here. Oops. Let's say I am going to give you a review. Okay, I like this food. It is really good, but uh, while delivering, the package was bad. Okay, so this is the context. Okay, so now if someone asks me to create a model that can able to give the sentiment of this particular text, which means sentiments like it is a whether it is a good review or a bad review. Okay. So in that case, obviously, I have to, read the entire context. I should not be seeing only this last word or, the last few words. Obviously, when I go with just the last few words, what will happen? This is a negative keyword, which means that I'll be like, I'll be saying this as a bad review. But instead, this is a review which is focusing onto the service provider. That's your Amazon or Flipkart or anything. But when it comes to the food, we see that I like this food and it is really good, which means that I have a very good positive review. How do you find it? Like this is a good information and this is a food product and I can maybe like, point this out and say this is a food product and he's liking it and it's really good. But sometimes people, mock it. For example, you would have ordered a food and they will be saying like, I like this, maybe I like the stones in the food, sarcastically people can write it. I like the stones in the food. So which means that obviously the model should detect the sarcastic meaning behind it because the context of the product should be brought into this account. That's one thing. That's one more, a thing which the model has to memorize. And it also have to process the entire sequence step by step to understand what is the key important words here. What do I need to keep in mind? So that is where, things will come very tricky because when I push this as a normal feed forward network, what happens? I kind of tokenize all these words and I push it as a very big word. That's all. So it doesn't have any meaning because you're going to stack every numbers together. So sometimes, some interchanging like might happen with because of the grammatical error. For example, it really is good. That is also, makes the right meaning. So which means that the number might change in between, but the output will be the same. So the model will find it very difficult to to even understand like what really happened. So that's where, as I told you, we require a model that can go sequentially, step by step, and not losing anything behind and not leaving the current statement as well. So it has to keep every of these things in mind. So that's where this recurrent neural network comes into play. And mostly, recurrent neural network has lot of applications, I would say. One of this, one of the most used applications like image captioning. This is becoming very famous now. Image captioning and text to image as well, where you will be giving an image or a text and the output would be either it will be creating an image or it will be giving you a text. For example, if you have an image that has a player or maybe a person wearing a jersey and he's holding a football in his in his leg, which means that it is very evident that someone is playing football. So when I give this image as an input, that image or it has to give a text output. Okay, so that is also a process of recurrent neural network. So which means that it has to process some sequential data and it has to give you some insights about it. Similarly, sentiment classification. So whatever example which I told you now, let's say you have a review, you have to understand the review and see like which one is like which which review is good and which review is bad, like that. So like likewise, you have only one input, and you might be having many sorry, you'll be having many inputs, but you will be having only one output. Okay, that is your true or false or something like that. And sometimes you also have this many to many context where a classic example which I would say is the translation. Okay, so English to Tamil, English to Hindi, or or any language to language conversion. I'm pretty sure that 10 years back, when you were doing this translation from from your native language to English, or English to your native language, many words will not be very effective, or let's say the translation will look very, very worst. Yeah, I guess many would have found that really bad during those days. But nowadays, the translation is really, really cool right now, because of the fact of the invention of the recurrent neural networks and transformers and other bigger large language models. Nowadays, the translation is becoming even more powerful in nature. So the translation is really, really simple and effective nowadays. That's one thing. And you do also have this many to many classification, where you kind of understand the activity done by a user. So this is also evolving right now, as you know that by based on the webcam footage, we can understand whether the crowd is uh, engaging in a fight, or they are just moving, or you can understand many of such activities just by understanding the videos, frame by frame, acting each and every frame, and understanding what really happens every frame. And you can able to give a sentence, or even you can give an output of what are the activities you have done in the past 1 hour or something like that. So likewise, I would say recurrent neural network has lot of different real-time applications, I would say, than in terms of images, or in terms of a feed forward network, that is your normal neural network and CNN. So that's where recurrent neural network has become a vital part, and people start to utilize it very effectively as the days goes on. And the fundamental building block of recurrent neural network, as I told you, since it has to like process the previous data into consideration, you can see there will be a mark, an arrow mark, that goes recursively inside each and every input. Okay, basically, if you have a normal network, it will be having this input and you have an output. That's all. So let's say you have an input and you have an output, but in this case, this will go recursively, and it will be handling word by word, or a sentence by sentence, or something like that. Okay, so that's the beauty of recurrent neural network. Let's just go a little bit deeper into this recurrent network, like what is the formula behind it. Okay, so this is the formula. Okay, so for a normal network, what's the formula, right? So it will be like h is equal to f of w plus x of t. You don't even have an x of t, okay, because you don't have a time period here, right? So which means that it will be your activation function with respect to weight and with respect to the input data. That's all. This weight and this data will be multiplied against each other, and you'll be getting some output. But this is the actual formula for a for a feed forward network. But for a recurrent neural network, as I told you, okay, so this will try to consider the old state as a part of the input, which means that you can see here, I have h of t, which is equal to f of w. That's your activation function with weight. And inside you have two things. Okay, one is your old state input and your current state. So that's what, as I told you, recurrent network considers the old state output or the input into consideration. Because of that, more insights can be gathered with this recurrent network. Okay, so that's the essence of this sequential model. I'll just expand this formula even more better to make you understand it little clearly. So when I expand this thing, this is the activation function, and this is the weight, and this is the input data, and this is the weight, and this is the current data. So this is the present data, and this is the past data. Okay, so present and the past data will be combined against each other, and it will be like aggregated together, and we'll be having an activation function to do so about it. Finally, you'll be getting this h of t. That h of t will be considered as the output. So now, one simple thing would be like, let's say, for example, I have this x1, okay, and I'm having the current state. For example, this x1 is the current state, and this h of 0 is the previous state. Let's take this case. Okay, so this is the first input which you're going to give to the network, which means that h of 0 will be empty. Okay, so this will not have any data because the previous state is null. because you are the start of the stage. So now with this two data, you'll be creating this h1, correct? So with this f of w, you're gonna like process this both x1 and h of 0 together, and with this particular weight, you're gonna push everything together, and you're gonna get h of 1. Now I'm gonna pass this h of 1 and the next data. So whatever which I have here, x1 and h of 0 will be combined together, and that will be forming one output. And this output will flow as an input to this next stage, where I'll be passing the next input here. Okay, for example, this is like I am good. Okay, so in this case, this I will go inside. Since there is no previous state, this will be empty. So mostly whatever h1 you're gonna get will be associated only with this I, correct? And now this I goes here, and am is also entering as a present state, and you'll be getting h2. Now this h2 will be an aggregation of these two words together. This will have the aggregated result of this I am. And finally, I'll be having x3. That will be the current state now. And this aggregated output h2 will be forming as the input, which is the old state input. Okay, the old state, the current state will be applied, and you'll be getting h3. Likewise, it will flow on and on and on to get the right output out of it. Okay, so this is how the flow will look like. So basically, you have some words, and each and every word will be assigned as unrolled as one present input. For that present input, you're gonna mix the previous stage outputs together as a part of your memory bank or something like that. Okay, so this is how a computation will happen, okay, during the time of recurrent neural. The only beauty of this is you will be having a shared weight. You don't want a weight which is variable towards each and every inputs. That's not going to happen. You'll be having a common weight for all this input roles. So that's one more thing which you want to keep in mind. Okay, so now similarly, the loss can be calculated sometimes, only sometimes, for some application. For each and every word, you might be having an intermediary output as well. For example, your language to language translation. Let's say from I am good to some or hello to Spanish, which is hola. So which means that like x1 will be hello and y1 will be hola. So likewise, hola como estas, like which means like hi, how are you, and hola como estas, which means that I'll be having each and every word. For example, for hi, I'll be having hola, and how are you is going to be translated as como estas. So which means this, for this x1, I'll be mapping this y1. For this x2, I'll be mapping this como. And then for this x3, for that is like u will be mapped against estas. Likewise, if you have some intermediate output, I can calculate this losses, intermediary losses, and I can get an aggregate. If not, if you're not going to have any intermediary outputs, let's take your sentiment analysis, where you have a very, very big paragraph, but instead your output is going to be either it is positive or negative, or you can also find the emotion behind it. Let's say whether the text is intended to be happy or sad or angry or surprised or something like that. Likewise, you might be having a varying different output. So if you have one singular output, you will be calculating only one loss. If you have multi-output, you'll be calculating multiple loss, since you know the actual outcome of each and every word. Okay, so that's one more thing which you want to keep in mind. So as I told you, if you have multiple words, all these loss will be combined together to form an aggregated loss. Okay, so it will not again flow as a loss for each and every stage. You will be aggregating this loss, and with this aggregated loss, my weight will be updated as a part of back propagation. Okay, so that's very important. Okay, it's not like the weight will be updated for each and every word. The weight is going to be common, and similarly, the loss is also going to be very, very common for the entire RNN sequence. Okay, so that is very, very important. So for the entire word or entire sentence, or for any cases, all the weights which is going to be updated is going to be based on all the contents which you have, which means that the loss will also be aggregated and averaged upon, and for that average loss, you're going to back propagate and you're going to update the weights. Okay, so that is how an RNN will work. Okay, so so do you have any doubts or clarification here? So is this clear? Because whatever which we have seen here is a little different than the conventional methods, because we are rolling back and there is a lot of past data and present data. So if you want me to explain any other concept again, please do let me know. Or any doubts or clarification, yes, do let me know. Okay, I I believe there are no doubts or clarifications. Surprised to hear. Anyways, now let's go for the for the problematic area, because whatever which we saw is really good. Okay, so it can able to process a lot of data sequentially. That's a great thing. But there are a lot of problems which is present inside this particular concept. I'll just let you know. There is literally two fundamental problems. One is exploding gradients, and another one is going to be vanishing gradients. Okay, what is gradients? We know that while we train a model, we'll be having this gradient as a part of loss, right? So this gradient will be calculated, and you're gonna utilize this gradient descent to reduce this loss as much as you can. So the gradients are the numbers, literally the numbers which is contributing to the loss calculation. So when you have a sequential model, usually the gradient will explode, because you're going to sequentially update the same value again and again and again and again to aggregate a final loss. It's not like you're going to have an intermediate loss, because you're going to aggregate all the losses together to form one singular loss, which means that there is a high probability for the gradient to be exploded. That's one thing. And the second thing would be like the vanishing gradient. What is vanishing gradient? It is quite opposite to it. Sometimes the model doesn't understand the actual nuances of the data in the first 5 words. Maybe the last 5 words might have maybe might have a lot of meaningful insights, but since the first 5 words are very, very literally nothing, or doesn't create any sense to the network, you might having a diminishing gradient. Because of the diminishing gradient, even it will have a super effect on the upcoming words as well. So which means that at some point of time, the gradient will be lost, which means that the previous state will be nothing. So if the previous state is nothing, you don't definitely, like, it's not going to help for the model to evolve. So these are the two important problem when it comes to gradients, or let's say exploding and the vanishing gradient. Let's see, like, how do we tackle these guys? Okay, I'll just come to this point a little later. Okay, I guess I don't have that. So in order to tackle this particular problem, for let's say in order to tackle this exploding gradient, I'll just give you one simple ideology. I guess I kind of discussed this thing I guess last class, where we were discussing about the sigmoid activation function, correct? And tan H activation function. The sigmoid activation function will have a distribution of 0 to 1. So which means that the max is going to be 1 and the min is going to be 0. Mid can be 0.5. And this will be something like this. So it will be like minus infinity to plus infinity. Whereas a tan H is also very similar, but you will be having the negative direction. That is like this will be -1, this will be 0, and this will be +1. This is again minus infinity to plus infinity. Okay. So the only difference between the sigmoid and tan H is like tan H is distributed across 0 to 1, and sorry, sigmoid is distributed across 0 to 1, and tan H is distributed across -1 to +1. And you do also know about redo, which is like which has like this. That is like x is equal to 0 if the value is less than 0. If it is greater than 0, x is equal to y. So that's a distribution, like a linear distribution it has. So for all these cases, okay, so since we have recurrent neural network, which is going to go block by block, word by word, and calculate the values, gradients again and again and again, you can visually see that sigmoid and ReLU has only the positive numbers. So if there is 1, okay, so in the next sequence, this will increase to 2, and this will increase to 10, and this will increase to 100, because all the numbers are positive in nature. So since all the activated value, the output value of these activation functions are positive in nature, your number will increase a lot. Okay, that's where we come to the standards, because you have a negative dimension as well. In that case, this will be regulated, okay, because of the fact, even though it goes to 2, it will be again regulated as minus, some negative numbers will be provided, and this number will not be exploding at all. It will be staying inside the bound between -1 to +1. So that is the advantage of using a tan H over sigmoid or any other activation function when it comes to a sequential network. Okay, this is very important because tan H kind of solves the problem of exploding gradient. Okay, so I hope this is clear, right? So this is one problem. And the other problem, as I told you, like, we have this vanishing gradients. So vanishing gradients can be removed by, increasing the memory power of our network. Because in this example, okay, I'll just, take this example. I have this review. Okay. This is the review. And you can see the review states that it is stating some about this product. Okay. Life original box of cereal. Okay. So it's a Quaker Oats. So what they have done. So the review is like Thanos is giving a review. That's really good. So here you can see that the review stands like, amazing. This box of cereal gave me a perfectly balanced breakfast, as all things should be. I only ate half of it, but will definitely be buying again. So in this, in this particular statement, it is very, very evident that, uh, I don't require these words, correct? I don't require these words because I know this is a box of cereal. Why do I need to again, understand or waste my time in understanding this thing? But yes, it is a perfectly balanced breakfast, which is a good thing because it is kind of contributing to the nutrients which is inside the cereal. That's one thing, as all things should be. And yeah, we all know that all things is there since it has the perfectly balanced breakfast. And I only ate half of it. I don't mind if you're gonna eat only half, or you're gonna like waste it out, you're gonna play with it. I don't mind. I just want to know the quality of it and if you are willing to buy it again. So in this case, he's saying that he'll be buying it again. So I would say the things which is marked in, in a bold letter, amazing, perfectly balanced breakfast, and will definitely be buying again. Only these are the contents which is very, very, very important. Correct? Now let's see like how does a recurrent neural network, process this. So as we know that it will be having the present state and the past state. For example, the past state is going to be empty. So for this, it's going to process this two data and you'll be getting an output on a H1. Okay, so this H1 and this will be, present state and this will be past state and it will be processed and you'll be getting an output as H2. This H2 will be again matching against this box and you'll be getting this H3. Okay, likewise, H4, H5, H6, H7, H8. So this will be processed again, this perfectly word will be processed against H8. What is H8? H8 is an aggregated value of this entire line that contains amazing. This box of cereal gave me. So there are a lot of words which is there. And, each and every word is kind of added against each other, which means that obviously that's at some point in time, this amazing will be, will not be really, taken at all because you have a lot of words which you have added as the sentences grows, which means that you might be having a negative impact of this particular sentence. I mean, this H8 will not be that effective because you have 1, 2, 3, 4, 5, 6, 7 words which is not really effective or which is not a positive word. And this one word against 7, obviously 7 will take charge. So this H8 will be very very, very negative. So you're going to compare this negative against this perfectly content. And then again, you're going to compare this balance against this entire content. Now, this amazing and perfectly will be 2 words against 6 words. Again, this will play. This will, play a vital role. Again, this balanced breakfast, everything will become negative at some point in time, correct? Because, there are a lot of negative words. Since there is very, very less positive words, when I aggregate everything together as a sequence data, you might not have a greater weightage here. And again, you have a lot of negative words again. I mean, it's not like negative, it's like a neutral word. And finally, we will definitely be buying again. So at this particular word, at this final word again, okay, you're going to combine this entire content. You're going to combine this entire content as one single, one single block. Maybe that can be H20 or something like that. This one single H20 is going to give against this again as in data and it's going to process. So obviously the aggregated output of this entire content is going to given as the input for the final word. So obviously, a lot of things would have been forgotten, right? So it's like it doesn't have a memory to, process which word is important because everything kind of mixed together right now. Every word is mixed and you might not know which has contributed to the learning at all. So the model will be more confused like, okay, which is important, which is not. So they'll become lot of dynamo. So that's where a lot of problem came into play because when the sentence size increases, let's say if I have only this is the sentence size, maybe I might have a good chance because you will be limited with 10 words or maybe 5 words or something like that. And you might be having some good, easier sentence to deal with. But, reviews can become little bigger and bigger in nature, right? So in that particular case, obviously, when the number of word increases, the tendency for the model to learn will becoming more and more a problem. So that's where RNN failed miserably, guys. Okay. The concept is really great because back in those days, taking 3 to 4 words is a really great thing to do with. But RNN doesn't suit our real-time situation because in real time we'll be dealing with a lot of words. So how did they tackle this problem? That's where we utilize a concept name LSTM. Okay, long short term memory. What is this long short term memory again? So it is a technique where it can able to hold data as a part of memory, which means that let's take the same example. When I run the same statement with an LSTM, that is long short term memory, long or short term memory. Okay, so that's how they kind of say. In this case, I can either, I can fix a memory block. For example, I can fix 40 or maybe let's say 14 LSTM blocks. Okay, I have 14 LSTM blocks, which means that this LSTM blocks can save words. For example, if I feel like this amazing is a very, very important word, that word will be stored in one of the blocks. And now this box of cereal gave me, these are like not at all important to me. This is like a neutral word. I don't want to save these guys in this LSTM block. And now perfectly balanced breakfast, all these things can be served in this LSTM. Again, there are a lot of neutral words. I'm not going to take it out. Maybe this half might be a problem because, the context is not taken, only the word is taken into consideration. Maybe this half can be, given here. And finally, definitely will be there and buying again will be there. So which means that all these 3 more words will be there. So likewise, all the memory, all the words will be stored in terms of memory, which means that it can able to store a long-term memory, like amazing. That's the first word which has been stored. It can able to hold that, for a long time. And you can also store a shorter data also. Let's say buying is a very, very, short-term memory because it is the last before word. So which means that it can also be handled. So which means that this particular LSTM block can able to serve or maybe can able to save data as in a longer term and short term, which is like whenever or whatever words are very important in nature, I'm going to save and I'm going to keep that in reserve so that I don't want to forget. I don't want to, mix every word together to form a bad meaningful insight. Instead, I can able to store those words. I can able to store those, each and every important words into the blocks. That's how LSTM, gain a lot of attention here. And you can also see like this is how an LSTM, one singular LSTM blocks will look like. So basically what happens here is, okay, here you'll be having the old state data. Okay, old state data. And this is the current data. Okay, so what really happens here is, the distribution of sigmoid, right? Sigmoid is either 0 or 1. And what is for tan H is like -1 to +1. So now this sigmoid is very effectively used here to make sure how do we stay or like how do we store a current data or how do we delete it. Okay, so very well, you can see it here very well. Okay, the input data is passing through here. Okay, if I feel like this old data is not important to me and the current data is very, very important to me, I can make this distribution as 0. Okay, even though the current data flows inside, I don't mind. I'll be making this as 0. What will happen now? 0 multiplied by anything will give you 0. Now, this region is called as cell state. This is like a memory lane of the entire LSTM block. And this is your input gate. This is your, I guess, store gate, and this is the output gate. Okay, so which means that the input which is processing inside, this is the old output and this is the current input. If the input is very important in the old input, I can mark it as 0 and make the 0 here. Or if I feel like the input data is not really important, it's like a very neutral word, I will make this as 1. So that 1 multiplied by anything in the old data, the entire old data can be whole data here. Okay. Now the next state. So this is where the deleting process will happen. So let's say if you want to delete the old data or not, or you want to keep it, you can, you activate this gate to delete the older value. Now in this case, now let's say if you feel like the new data is very important to me, okay, if the new data is very, very important to me, what I can do is I can make this as one. If I make this as one, what will happen? This will be one, and the entire data is going inside the standard activation function. After it will be going to be multiplied with this one, which means that again, the same data is going to pass here. It's going to add against this data. So if the old data is empty, okay, it's like a, it's like a good sign because empty data is going to add it. But sometimes, you can even add both the data together, because obviously you will never get it as zero. It will be like 0.1 or 0.2 or something like that. So a partial amount of old data will also be there with the new one. And again, this will not be entirely one. It will be like, 0.8 or 0.9 or something like that. So in that particular case, partial, 80% of the data will be passing around here, which means that, yes, I can control this by using the sigmoid, whether it is important or not. And finally, if I want to make sure this data have to be passed to the next layer or not, okay, if I want to give this importance to the next LSTM block or not, I can decide it here. Okay, what I can do is I can make this as 0. This area as 0. If I make this as 0, what will happen? 0 into anything will become 0. So which means that no data will passes to the output region, or maybe lesser amount of data can also be, let's say if I can keep it as 0.3 or something like that, less intense data will be flowing here. Else, if I make it as 1, whatever data which I have will flow to the next LSTM blocks. Likewise, the LSTM blocks will have a tendency to delete, to hold, and even how much amount of data can be pushed to the next sequence or the next LSTM block. Okay, in this way, it has a very good flexibility to store the data, and it can able to handle a long sequential content as well. Let's say a long sequential content like 20 words or 10 words or 25 words or something like that. But yes, you cannot go beyond 10 or 15 words, because that is again another big problem. But nevertheless, LSTM was a successful thing because it can able to handle a bigger sequential data than a normal recurrent neural network, and it doesn't have this vanishing gradient problem at all, because of the fact it can able to hold memory in a longer term as well, whereas normal RNN will not or cannot do that. Okay, so that's the basic essence behind this LSTM neural network. Is there any doubts or clarification at this point? Okay, so I guess things are a little clear now. But again, even though I have a highly skilled network now, still it is a sequential network. I will say one thing. Okay, so as I told you, LSTM can able to handle a longer sequence, but it cannot handle as ChatGPT. You can give maybe like a 50 word or a 100 word sequence as well as an input, correct? You can give a very, even like sometimes I guess the limitation is for the trial version. For the pro version, you can even go with 1,000 words as well. Okay, you can go as long as a 1,000 word command or 1,000 word content. ChatGPT can able to do that very easily, but not the LSTM guys, because LSTM has a limited, advantage. Yes, it can able to handle a longer sequential data, but ChatGPT can able to do it even better. Okay, not ChatGPT, another different models, or let's say it is required to have a model that can able to handle larger amount of data. And again, you would have noted one more thing. Let's take this RNN into consideration. I'll just go back some slides. Yeah. Now, let's take, I have 100 word sentence. Okay, I'm going to process all those 100 words. Now, what happens now? The first word will be going here, and you'll be getting an output for the first word, and the second word will be here, and you'll be getting the output here. Likewise, it goes on and on and on and on until you get the 100th output, which means that I cannot process this 100th data unless I get the 99th output. How do I get the 99th output? I have to process the 99th input. Likewise, like I have to wait for this output so that I can process the next one, which means that even though you can, improve the power of GPU and do a lot of wonders within it, the problem is here it is very sequential. Only when you get the output of this H1, then only you can able to process this X2. Likewise, only if you get the output of this H2, then you can go with this X3. Likewise, if you have 100 words, you have to wait for to process this entire 100 word, because you cannot parallelize this at all. Even though you can use GPU or anything, this is a sequential process. So if it is a sequential process, it's gonna take lot of time, because it's I'm talking about billions and billions of sentences, very large context of data, because datas are very important in this NLP standpoint, because a vocabulary can change the entire, a single word can able to change the entire sentence. And a lot of people will use rich vocabularies, and some people might use a limited set of vocabularies. So it has to handle all these kind of vocabulary set together to make some meaningful insights. So which means that it is going to be very tough for a model which is sequential in nature. It will take definitely more amount of time to train the model. So more amount of time, I'm talking in terms of weeks and months. If I have billion words or billion sentences with me, and I process using LSTM or a normal RNN technique, definitely it will take months to train the model. Even though you have lot of GPUs with you, you cannot parallelize this work, because each and every sentence is to go have to go through every word accordingly. Because without the previous output, let's say without this H1, you cannot process this X2 at all. So you have to wait till this block is done, then only you can go for the next block. Likewise, the 100th block cannot be executed unless and until the 99 blocks have executed successfully. Even one block fail to give you the output, or some problem happen, it can never process things parallelly. So this is the biggest shortcomings of a normal sequential network, that is like RNN, LSTM, or even GRU is there, gated recurring unit. So that is also very similar to uh, LSTM blocks. But yeah, so basically, yes, this have a good advantage. This can able to handle some amount of data, but not to a larger contents like we expect right now. That is where a miracle happened, I would say, in 2017. The stage we are in right now, where we utilize this OpenAI's Chat GPT-4 or GPT-3, or there are different models which is available. It is all because of this one single paper known as Transformer. Okay, Transformer, as in the name, attention is all you need. Okay, I'll just show you this paper. It's one of the interesting paper. Definitely you have to give it a read. Just type attention. It's all you need. They also have a GitHub account, GitHub repository of the entire code base. You can be able to access it. I'll just show you this content. I'll also give you this link. Please do read if you want to understand more about what happened, because this is where history started. Because this has been published by Google Brain and someone from the University of Toronto. Most of them are from Google's Brain and Google Research Department. Everyone. Okay, Ashish Vashani was the the main contributor of this of this particular paper. You wouldn't believe. I'll just search this Ashish Vashani's feed. You can very well see that or he or she would have a very greater future, because all these people have been absorbed by many one. For example, you can see she's a co-founder of some stealth startup, and co-founder, chief scientist of some. So there are like all the people who are in this paper had landed to greater jobs, or they have started their own startup, because this is a very a potential breakthrough in terms of NLP. Okay, for NLP, as I told you, this RNN was the extent which they can able to rival till 2017. Till 2017, there is no subsequent improvement in RNN at all. So that is why we didn't even had a chatbot in 2017. But post this attention is all in it. Post this transformer architecture, but okay, everyone started to create their own chatbots. I'm not sure like whether you know it or not. In 2018, a lot of chatbots, was becoming very famous. Everyone started to say what is chatbot, and even I would say AI has become very famous because of this chatbot, I would say, because at some point, because nowadays you can literally see like all the banking sector has this chatbot, right, enabled into it. Even when you like, go to a customer care, for example, you're going to like, call to a credit card department, you explain all the worrying things, for the, to the customer care, and they say, this is not from our department, I'll, switch you to another department. And you have to repeat the same statement again and again and again until you find the right guide to, to deal with. So even they have automated this. So they'll be asking like a short sequence or short text to summarize your problem. If you say that, it will correctly connect to the right department. Likewise, many such chatbot based applications have started to evolve because of this paper. And even the chat GPT, which we see, GPT stands for, the last T stands for transformers. Okay, so transformer is the essential stepping stone of the current stage we are in. Okay, and this is the paper. I also just give you this link. You can just give it a read. It's one of the, a very useful. Sorry, I will tell everyone in meeting. Yeah, just shared it. You can, read this paper. This is a very useful paper. Okay, I'll just teach you what really happens inside this transformer for sure. Don't worry about that. But this is the architecture. I'll just, I'll just say, because of this transformer, a lot of potential, things came up, because transformer can able to handle data parallelly and not sequentially. That is a huge boost, guys, which means that I can able to handle data parallelly, which means that I can train my model really fast, then waiting for the sequential data to be ending, against each other. And which means that I can even go for a longer sentences as well. Let's say 1,000 words or 1,500 words or 2,000 words also. I don't mind, because I can, as long as I have this parallel capability, I can train things really fast, because I don't want to wait for 2 weeks or 2 months for the model to get some output, and you will be seeing the model is not performing really great. So it will take, too much of time to research something out of it. So that means attention is all in is one of the important paper that, broke down the history of how things have handled in terms of a NLP data. And similarly, it has a very high accuracy. It's not only that it can able to handle sequential data parallelly, it has a very greater higher, it is having a very high accuracy, so that it has started to replace all the conventional methodologies like RNN, LSTMs, or GR or anything. Okay, now let's go into this, transformer architecture in detail, because this is the stepping stone. As I told you, this is the important architecture which you want to keep in mind, because everything which is, built on top of this. Okay, basically. So here you can see transformer usually have two blocks. Okay, one is the input block, another is the output block. It is like, input is going to be the actual sequence you're going to give, and output is going to be the expectation. Sometimes the expectation can be labeled. It can be, positive review versus negative review, or emotions. Emotion, let's say happy, sad, neutral, bad, all these blah, 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 plus. Okay. Sometimes the input can be English, and the output can be, Spanish or French or something. So you should be making sure to segregate the input and output. Okay. Now, in this case, you have, basically two blocks. One will process the input data and one will process the output data. The only transfer which happens here, some data is transferring from the input block to the output block, and you're going to get some output as in the form of this softmax. Okay. So that is how things will go. Now let's go a little bit deeper into it. Okay. So basically, usually what happens in RNN, we give a word, the word will be, created, will be utilized in RNN, that will create a certain embedding matrix. You know about this matrix, right? This embedding vector, which we saw in the previous class, so it is very similar to that. But the thing is like this embedded vector will be even more very, very accurate. As I told you, this word to vec corpus has increased a lot with a lot of billions of words into it. So relevant numbering will be given. Okay. For relevant words, relevant numbering will be given. So here you can see like, for RNN, I have to process word by word, but for the transformer, I can give every word together and I can get the, numbers subsequently just like that. That's the advantage of using the transformer. Now let's see like how this is created. As you know that, word embeddings, right? So you have a word and you try to embed and give the right number to it, which should be, very close by to each other. For example, human, sun is very close by, guitar, violin, and viola. Viola is not very close by because guitar and violin is one, one category. Happy, sad, love. Red and sun is somehow a little closer because sun is red. or as a dog and cat is a little close, but or have a little bit of a bigger distance, but as it is also like kind of grouped against each other. So likewise, embedding space which has been created with this word to vec, which is also, which was developed in 2017, I believe. No, sorry, it's in 2015. And with this, bigger, larger corpuses, they can able to, get the right input embedding for each and every word. Okay. Because of this, feature transformation only, I can able to, create the right number. So you can see one important use case here. AJ's dog is a cutie. AJ looks like a dog. So you can see like both the contexts are very, very different. Even though I have a very powerful embedding space here, but that doesn't make the fact this dog and this dog is not the same, because this is representing the dog and this is not representing the dog, which is representing the nature of the dog. So now the position of this word is also very important to me, correct? Because the position of the word totally changes the entire sentence. So which means that even though I kind of, get the right embedded number, it is not enough, because I need to understand the contextual information of the current word for the current position. If the position changes, what kind of context changes? So that is one more important, that is one more importance which has to be given here. Okay. So simply put, I have some words. Okay. And those words can be anywhere in the sentence. And based on that, the entire context will be changed. So I have to find a way to position that as well. So that's where, this transformer kind of included a concept known as position encoding. Okay. This position encoding, it does very simple thing. It kind of creates the position for each and every word. For example, AJ's is position number 1, dog is position 2, is position 3. Well, let me like write it out. This is 1, this is 2, this is 3, this is 4, and this is 5. Similarly, this is 1, 2, 3, 4, and 5. So now for this sentence, this dog is in position number 2. And for this sentence, the position is at number 5. Okay. So which means that when I have this position in mind, okay, I might have more insights about the sentence, correct? Instead of not knowing the position, okay, and just focusing on the word alone might not give me good result. But in this case now, I can able to have, different words at different position, and I can, if I can able to note the changes of the position, and if there's a very big contextual change, I might, keep into consideration, which means that whenever the word dog comes in the second position, I get this kind of context. Whenever the word same dog comes in this position number 5, I get a totally unrelatable context. Likewise, I can able to keep that in mind. So that is where, this positional encoder came into place. You can use any kind of positional encoder. Okay, it's basically, a sine or a cosine transform, given the data. Okay, so now, basically what I'm going to do is I'm going to take the embedding of the dog, of the word dog, and I'm going to add this positional encoder together. Okay, now the embedded, the word to vector value which I'm getting will be added against this positional encoder, and you will be getting a number which is also a vector. But this vector, this particular vector has positional information also, which is like, context info. This particular word dog now has the context info, like where it is present. So that will create, a totally a different insight about the particular word. Instead of, blindly going for this word, I'm going to give a vector space like this. And for this word, I'm going to vector space like this. And if the word comes at different places, you'll be assigning the same vector space. That is wrong. But in this case, since I've had this positional encoding, I might even have more insight about like where it is and what it is doing and how it is changing the entire context of the context. Okay, so that's where this positional encoding came into play. Now you can very well see the first block of the transformer, that is your encoder block or your input encoder block, where you can see the input is given, right? Yeah, sorry. The input is given, embedding is done. This is normal embedding. Okay, normal word to vec or larger language model vectoring. And then you have a positional encoder. Okay, you have a positional encoder. And then once this positional encoder is done, I'm going to push it to a multi-head attention network. Now, what is this multi-head attention? Because that's the essence of this particular concept. Okay, so it is simply put, what we do is first we'll try to have a concept known as a self-attention, which is like, I have a word and I have the same sentence that contains this word, and I'll be, saying which part of input we should focus more on. Likewise, for example, if I compare this the against this entire word, obviously self-attention will focus more on the same word. Likewise, for this big, I'll be focusing more on the same word. Likewise, this red is focused upon the same, and this will be focused upon this. Which means that I'll be like, focusing onto the same word, and I'll be giving more attention towards it, and I'll be getting an attention vector, something like this. Okay. Now, this attention vector will say, for this particular word in the given sentence, I feel like this is important to me because I have the same word. I have the same word with me. I'll be focusing more of attention to it. Likewise, I'll be going word by word and I'll be giving this attention vectors. So what does this do? Is it really important to have the self-attention? Yes, self-attention will be there, but at some point in time, each and every word will be mapped against different words. Let's say a translation. This the will be focused against the actual translation happen. So which means that this attention vector plays a crucial role, because this is where attention mechanism comes into play. As you can see that the entire paper named as attention is all you need. You don't require anything. You just require the attention head alone that can able to do a lot of wonders. So where you can see here, sorry. Here you can see the data will be given. Okay, so all the data will be given parallelly. So that's the advantage. As I told you, here you can see like I'm giving the data and I'm giving, getting the embedded data, and you're going to take the positional encoding and get the output. So in this case, no context have been used from the previous one, which means that the word the is going to be independent against each other. Okay, so it doesn't require this big red dog at all, because I have take the first data, I use the position as 1 and I add it. If I go with the second one, I use a position 2, this is position 3 and position 4. That's all. Position is, relatively defined here, which means that I don't want to wait for any other word. Let's say for this last word dog, I don't want to depend on the entire 3-word output. Now I can, go parallelly. This can go parallel, this can go parallel, this can go parallel, and this also can go parallelly, which means that I can process that parallelly. Okay, that's one thing. And then once that goes, you're going to go into the attention network. Okay, and you will be like, having some normalization technique, to make sure there's no overfitting happening. And then you're going to add a feed forward network. What this feed forward network does? Usually, when it comes to any network, okay, you're going to have this feed forward network to dissolve it. Feed forward network has a very good dissolving factor, which means that no matter like how bigger the input you have, you can fixate the number of output you're going to fix. For example, in this case, the input is 3, but the output is only 2. You can fixate onto those numbers so that this will act as a dissolving factor. Usually, feed-forward network is used for dissolving. Let's say if you know CNN, convolution neural network, you'll be having multiple different filters or multiple different, feature maps will be there, but finally, you'll be having a feed-forward network to dissolve it. Okay, so that's where this feed-forward network comes into play, and you're going to have some more normalization. Okay, that's one thing. Now, let's go for the decoder block. Okay. Now this decoder block is very similar to the encoder block. The only thing is like you're going to pass the expected output. Okay, you're going to pass the expected output. You're going to have this data and you're going to have the position encoding, and you're going to push this data. And when I push this data, I'll be having a concept known as masked multi-threaded attention. In this masked multi-threaded attention, I'm going to mask the actual input data itself, because if I don't mask that, self-attention will take place and it will give more weightage to the same data again and again. So that's why I mask it. Whatever data I'm going to give as input, that data will be masked, and the remaining data will be given for the attention gaining. And after that, okay, here, that particular multi-attention will come here, and whatever multi-attention output which I got in the input will also join here. This is like encoder decoder block. Okay, this block can be termed as encoder decoder attention block. Okay, so you can see you'll be having something like this. The input is the big red dog. For each and every word, you have the attention vectors. And similarly, this is like for French, Lagrange chain row. So which means that for the you're gonna add le, and for big you're gonna add gross. So which means that like it will try to match against each other. It will say like for this particular word I have to match this guy. For this particular word I have to match this guy. But sometimes sometimes simple words would have been swapped. Some words, maybe this chain would have been said as dog and this red is rogue, something like that. Or maybe this gross is red and chain is big. something like that. So sometimes, in languages, they interchange words. A big red dog and the dog is big, or some words they form it a little different. So likewise, I have to gain my attention. This word belongs to what kind of which part of the output, or if there's a two word and there's only one word output, means yeah, how do I mark that? So how do I gain attention of which is the input and output combination? That's very important. Okay, so that's where you kind of I'll just see, like, this big red dog is given as input, you get the output, and you're gonna, like, get the output go on running, and you're gonna add this in encoder decoder block together. And finally, as usual, I'm gonna go with the feed forward network to dissolve it again, and you're gonna have a linear network. This is also again another feed forward network. Again, I'm gonna dissolve it, then I'm gonna have a softmax, and I'm gonna get a probability output just like that. So simply put, I have the data, I have the output, I'm going to do this attention mechanism, okay, and then I'm going to get the output, and both the attention vectors is going to map against each other to form which is important to me and which is not, like which word will be formed against each other. And once it gains a clarity, it will go here, and just like that, it can able to do all these possibilities. Okay, so this is how a transformer usually works. I have one more thing would be like, what really happens in this attention mechanism is like, this is what happens. We have this VKQ. V and KQ stands for, the sentence or the keyword and the query data. So based on that VKQ, you do a scaled dot product and you get an attention, which is the formula. This is how the formula will look like. The Z which you get is a vector that is known as the attention vector. Okay, so now without having the with just having the attention network, I've just did a self attention network, and since it has multiple words together, this is why we call this multi-head attention. Okay, because you have multiple input and output to be considered, and that will be compared against each other. Okay, so that's how you can see that. So for one data, you have one output. When you have multiple data together, you're going to stack it together, you get a multi-head attention network. Is this clear? Any doubts or clarification? I know this is a little bigger. If you want me to know, say it in even more simpler words, to let me know. I'll just repeat it again. But this is how a transformer will look like. Okay, this is what changed the entire revolution of the, of our model understanding or such like that. So is this clear? Any doubts or clarification at this point? Okay, so I guess there are no doubts, surprisingly. But just do watch, do read that particular paper, because that will give you more insights about this thing. So now, because of this transformer, you can literally say there is no limitation, right? Because you can form as many number of words as you can, because you're just going to map each and word against each other. It means I have a very big sentence, I can also compare against a very big sentence together. Or sometimes you have a lot of sentence, you have only one word, that is your sentimental analysis as well. Likewise, you can match encoder decoder block as per your applications flow. Okay, so apart from that, yes, it's not only this transformer does not only help your NLP community, it also helped in terms of images, because that's where this text to image generation and generate image to image captioning on all these things have become very popular because of this vision transformer again. So this vision transformer was introduced in 2022, which is very recent. Okay, where they have created a very, very similar strategy. Instead of text, you have image, but this image is kind of patched. Okay, you can see this is kind of patched together, and this patch plus position and embedding is done. Usually for word, you're going to have only the position embedding, but here it is a form of a patch, right? So patch and the position of the patch is kind of embedded together. Okay, so it's kind of embedded together, and you have a transformer encoder block. It's not like it's not like encoder decoder block. It is only transformer encoder block. Okay, you're going to encode that data alone, and you're going to have push it to an MLP to get some output out of it. Okay, so that is how this has been created. Okay, so likewise, basically, for this transformer model to work again. So basically, when you want to make this model to work, there's one more bigger challenge here. What is a bigger challenge? It requires more data to proceed. It is very, very data hungry because it has to understand the mapping between the same words again. And because let's say I have a dog here and I really don't know which word usually say we can say it as dog. For example, I'm not sure whether it's gross is dog or chain is dog or rogue is dog. But certainly I have a gut feeling that this dog will be mapped against dog. But we don't know that, correct? I'll just check it out for out of curiosity. English to French. I'll just put it as dog here. It's totally different. Oh, sorry, it is dog. Chain. So you can see, right? Dog is mapped against chain. What about red? Red is rock. Correct? So I'll just put the entire word, the big red dog. Lagrange chain rock, which means that we were thinking that, correct? We were thinking that this red is mapped against chain, but when I go with individual words, let's say dog alone, it is chain. If it is big, it is either grand or maybe I'll just, reverse it and see what is gross. It is fat. See, this is what happens. So even though this big is not clearly indicating this word, but usually in terms of French, okay, in terms of French, they will say it as it's a fat red dog instead of, how we say it in English, it's like a red dog. In their language, they will be saying, mostly saying it as a fat. So that's how things will change. What about if I changed as rich? I can say it's a rich red dog or something like that. So likewise, even though this exact word is not, mapped against each other, the meaning is totally different, which means that it needs to validate lot of sentences like this. More sentences it can see, it will understand the word. Because like now we have Google Translate with us, we can able to map each and every word against each other. But here it is not like that. If I map each and every word against each other, what will happen? It will like Legros, or even though it will not be gross, it will Legrand rogue chain. It will be like, it will not have a meaningful sentence at all. But as in French, you have to say it as Lagrange chain rock. But here, if I map against word by word, the mapping itself will be totally bad. Correct? So that's the problem. And that's why we require more amount of data. And luckily, for an NLP, we require more data again, because more the data, more understanding can able to be brought into it. So that is where this large language model came into play. LLMs, large language model. So it's basically, just like, trillion words or a billion paragraphs will be there. All the paragraph, all the contents which is taken from the net, from the books, from YouTube translations, from closed captionings, from posters, all the different sources have been taken. And with the form of a joint learning, people started to utilize or create embedded vectors. This kind of encoder decoder attention has been created for all those words. So basically what they do is like, because obviously you cannot label everything together, na. So what they do is they do some specific translation operation like this, and they will be like, giving the first 10 words and try to predict the next 10 words, and the next 10 words will be given as an input, and the third set of 10 words have to be predicted, and it will be see like whether the third set of predicted output and the second set of predicted output is the same or not. Likewise, they kind of play pass all these data together to form a large language model. And as I told you, transformers are very, very data hungry in nature. This, more data paved a better way. But again, as I told you, if we would have gone to this LSTM blocks or something like that, this will take ages to train the model in the first place. But now you don't even, you don't want to wait for the entire word to be finished. Since you have transformed as a parallel processing, you can very well process it just like that. And again, they kind of, have an API mesh where they can able to, train small model together, and they kind of have a federated learning. So with the federated learning, they kind of average the, model performance so that every content will be, combine and merge together. So that's how OpenAI has done this, because they have a lot of different servers and they push the data, different types of data with different servers, and they train it, and they kind of add it together. So because of this large language model, people can able to leverage that particular pre-trained weights, and with that pre-trained weights, when you can able to create a impeccable method like GPT, GPT 3 or GPT 4, you can able to create a lot of wonders like this. So I would say the stepping part is the transformer. Okay, without transformer, nothing would have become a reality like what we have right now, because whatever which we see is like closer to artificial general intelligence, because whatever question you ask to the chat GPT or any kind of large language model, it can able to give you a generalized output, right? So that's that's one of the bigger or greater essence of utilizing this transformer. Okay, so that's one thing. So is there any doubts or clarification at this point? We saw a very deeper insight of how this transformer model works. So is there any doubts or clarification at any point, like what is RNN, what is LSTM, or how does this text is going into this, and how do you say this is learning like this? If you have any misconception in the concept, or a flow which is not clear to you, please do let me know, because with this we'll be like going to some hands-on part of how to construct some RNN networks and LSTM networks, and we'll also try to see like if we can generate some contents, maybe a word or something like, without using transformers. Okay, because tomorrow like we'll be focusing more on a transformer and so on, and prompt engineering using ChatGPT and stuff, but today is all about again basics. So any doubts or clarification at this point? Okay, so I guess there are no doubts or clarification. Okay, now let me go to the programming part. Okay, so now I'm going to like create a very smaller system, where I try to create a model with some context. Okay, I'm going to create let's say an emotion, or maybe how can I put it, a sentiment analysis, where I have some contents with me. The contents is all about directing sarcasm in the headlines of the newspaper. Okay, I have some 30,000 headlines have been marked. Okay, 30,000 headlines have been marked, and I'll also have a an output known as whether it is sarcasm or not. Okay, to see whether it's sarcastic or not. So each and every headline will be there, and the corresponding zeros and ones will be given. If it is 0, it is like non-sarcastic. If it is 1, it is sarcastic. Okay, so that's how I'll just I'll just run it. You can very well see that. I'm just cloning the data. Oops. And I'm going to print the first 10 lines. You can very well understand how does the data set looks like here. And apart from that, I'm going to use TensorFlow, library to convert the words, the sentence, the paragraph into sentences, and the sentences into tokens. And with that token, I'm going to create a sequence. And one more thing which you already know, that whenever you have a neural network, the input size have to be fixed here. Okay, so you cannot change the input size, which means that let's say obviously sentences might have different words. For example, one sentence might have 4 words, another sentence will have 5 words, another sentence will have 10 words, but I have to maintain all the sentences to be in a singular form. So either I have to pad the sequence. How do I pad it? I can add some zeros in the front, or add zeros in the back. Or if you want to trim it, I can remove some words. So likewise, I kind of removed everything here. For example, I have loaded this data, and I've given the tokenizer. I'm fitting all the words. I'm converting all the words into tokens. Take the word index, use the word index. That's going to be your, all the words which has been tokenized. And I can use a command known as text to sequence, which will automatically, make this as a sequence. For example, each and every word will be matched against the sentences, For the sentence, it will be creating some numbers to it. For example, you did saw in the previous example, right? Previous PPT where I am a good dog. For each and every word, we kind of create a token, right? A number. Likewise, I'm going to create a sequence of numbers and then I'm going to pad it. Okay, for padding would be like something like this. Let's take, yep, what happened here? Okay, something is not right. I'll just print this data. Okay. This will show you like, the first 10 lines of the data set. Yeah. This is how the data will look like. Okay. So I have serial number, article link. This is the article, link. I don't want the article link. I want the headline and I have the label to it. Okay. It's like former versus store clerks use over secret something. Okay. So it has a very big line. So I have non-sarcastic. What is, let's lead some sarcastic. The Bernard just want wife to listen, not come out. So likewise, they usually, put some sarcastic meanings, right? You know what is sarcasm, right? So it's like a double meaning. So even though they might have, pointing towards something different, they humorously, mock that particular thing. So understanding sarcasm is really tough. I know that even, human beings makes a lot of mistake understanding sarcastic, meanings towards it. But with this data set, let's try to see like how do we, make some, work it out to make it a little better. Anyways, I have like 30,000 of data, and this is how I have created the tokens. And there's one more thing which we called as OOV, that is out of vector. Usually, when you are going to create this kind of vocabulary set on your own without using the word vector, I'm just creating my own tokens. Okay, since I'm using my own tokens. Okay, so basically, I'll be giving numbers for each and every unique words. Okay, so in this case, you can see I have, close to 26,000 unique words, and each and every sentence, each and every headline has the maximum of 40 characters, 40 words. So if it is below 40, all those 40s will be added zero. So you can see this is one sentence where I've added like 308, 15, 115, 679, 3337, 2298. Likewise, these many words have been created numbers with word index, and remainings are zero because the sentence might be very, very small. Sometimes the sentence can be like, equal to 40. So they have taken an average of sentence value, and based on that, they created this matrix. So basically now this entire word or this entire sentence have been converted into numbers. Okay. So basically it is like a feature extraction, which we have done right now. So I've done the feature extraction and some numbers are there, and the corresponding output has also been given to me. Okay. So now everything is done. So I'm going to go with a very, very basic normal neural network. So, your basic feed forward neural network. I just wanted to show you how this model evolves. Okay. So that's a ideology behind here. Okay. So I'm going to create a very small neural network that has 40, 20, two layers of hidden, two hidden layers, and that has 40 and 20 neurons. And this is the batch size and everything. And beyond, what I can do is I can go with the validation split. Let me do the validation split is equal to 20%. Okay. Sorry. Now let me run it. Let's see like how it goes. I have a batch size of 100. Oops, what happened? If something is not correct. We run this guy. That is the input. Data of sarcastic is the output. This was a train function. Okay, this is surprising. I didn't thought this through, because the problem in Colab is like this is one bigger problem. So every time they kind of create different versions. Now you can see, I guess the latest version doesn't have this validation split at all. So I am forced to not have this validation split in this case. So which makes me not know like how the model is evolving. But okay, certainly let's see like how this at least the training accuracy comes up. Okay, let's see like how the training accuracy is. Okay, it is training for multiple epochs. And I don't see like it is increasing way beyond 56, right? So it is like, struggling as in same number like 56, 53. There's very, very less change actually. It's still staying at 56. Only this 41, 42, 43, 35 number, only the like last 2% points are being changed, but still it is struggling hard because a feed forward network doesn't treat the data sequentially. It will treat the entire data as one single content. Like say this content, whatever we see here, right? This entire content will be treated as one. So there are a lot of number combinations here. Maybe, as I told you, sometimes if the numbers have been mixed up, they don't even find it out. The feed forward will find it very difficult to understand the nuances of the data. That's where sequential, modeling comes into play. So let's see like how much different the sequential model does. You can also very well use spacey here, to remove unwanted words like lemmatization, stop words, and all these things can be done. Okay, that can be, one of your homework, which you can try it out. Since you already have the spacey programs with you, you can utilize spacey, cleanse the words, and then, try to train it and try to see if you can able to beat the results. Okay, so it is kind of stagnant now. Okay, now even though the model is not even growing, or there's no fluctuation at all. Okay, you can see the loss is kind of same. The accuracy is also the same, which means that the model lost its ability to understand the content. The nuances have been totally destroyed here. So it is very evident now. I guess now you can very well see, right, with a NLP content, multi-layer perceptron, your normal neural network is not even working correctly because of the fact it doesn't understand the nuances of the contents because it's not handled sequentially. That is a very, very big problem. So now let's go to this LSTM block. Okay, so I'm going to use the same code. Everything is going to be the same here. There's no big difference. The only change which I've done is this, program block where I have added this embedding layer, and then I've given this, LSTM block. I've taken 32 LSTM blocks here, and everything is the same. Okay, every possible thing. I'm going to go with 10 batches here. Okay, let me go with 10 batches, and remaining are the same. Okay, training labels. This is training label. Yeah. Okay. So yes, everything is going to be the same here. Okay. So now let me run it entirely. I'm gonna run it. So getting the data, converting the data into tokens, sequencing it, sentencing it, and padding the sequence together, and then you kind of have this LSTM blocks alone have been changed. Nothing has changed here. Only LSTM has been changed here. And let's see the output of this particular guy, because now everything is going to be handled in a sequential fashion. So which means that you might have a greater accuracy than the previous one. Let's see like how it goes. I guess it is importing TensorFlow and trying to read the contents out of it. Okay. Now let the model start to learn. You can see, right, with normal multi-layer perceptor, with the normal neural network, it was taking very less time to train the model, right? I will just show you. It was taking just 1 second, literally 1 second for one epoch and 3 milliseconds per step. But here you can see for one epoch, it is taking like 27 seconds and it is having 82 milliseconds per step, which is clearly indicates that the model is very, very complex in nature. As I told you, it is handling data sequentially here. Each and every data after process. So this is where the delay comes in. You can very well see here, right? This much delay is there. 27, literally 20 seconds, it's been, I know is taken to process this much amount of data. It's just, just 30,000 data. That's all. And with that has 40 sequences. If you talk about, lakhs, if you talk about billions, millions, trillions, imagine like the time taken to do this thing. But like one thing which I can do here is, let me, interrupt the execution. I can change the runtime type of GPU now. Okay. That's good. Okay. I cannot use those. I'm going to use Tesla T4 GPU now. Okay. I'm going to connect this Colab to a GPU. Because like I can boost the training at least somehow with the processing things, but the sequentiality will be the same. but at least like processing time can be a little faster. Let me run this with GPU. Obviously, GPU will play a vital role because without GPU, your training time will be even more bad. But with GPU, with the smaller size, I guess, it can able to do it in a very short time, like let's say 3 to 4 seconds, rather going with 20 seconds in terms of CPU. It might take some time to load the data again. Let us wait for that. Meanwhile, if you have any doubts or clarifications at this point, you can let me know. It has started its training process. And one funny thing is like you can see the estimated time is like, way above 20 seconds. I'll just tell you what is happening here. Okay. You can see a drastic improvement in the second up from the second epoch. Okay. Only in the first epoch, it will take more time, but after that, it's going to go very fast. It's going to go like, 100 kilometers per hour. You can see, right? The first epoch, it was taking too much time. Second epoch literally took 5 seconds. From 31 seconds, it has reached to 5 seconds. It will go even more faster, like 4 seconds, 3 seconds. This is what we called as GPU warm-up. Okay, basically, your CPU will be running every time. Okay, because you will be doing some process. But with GPU, GPU fans will not be running at all, and it will take some more amount of time to transfer all the data from CPU to GPU, because it's not like both the memories are totally different. The architecture is totally positioned at different places. So the CPU, whatever data which you have handled, it will be done using CPU. The CPU data have to be handed over to GPU. It's like a direct memory access. It has to be, establish that connection, and all the data have to flow inside the GPU. So for this, for the fan to run, for the GPU to warm up, and for all the data to traverse inside, the first epoch alone will take more time usually. Okay, for any network you're gonna do, always the first epoch will take more time. Let's say you can see like I guess like 6 times higher time. 6 higher times, but after that you can see like the model literally ran in 3 seconds in even more better. And a surprising thing you can see here is like the model reached like 100% accurate. Okay, it's like 99% accurate. I don't think so, but I'll just try and see like whether this validation split can be improved even here. Is that is running or not? Okay, surprisingly it is running, but I hate to stop it because I have to compile the model first. Okay, without compiling, the model will be resuming from epoch number 10. Okay, now let me run it. Now let's see the essence of it. But I'm not sure why it was giving me wrong, some error in the previous example. But now let's see like how the validation accuracy comes up. Okay, because I have a bad feeling because sarcasm is very tough and you have a very, very large vocabulary set and you are not using any embeddings at all. Okay, but yeah, so some basic embeddings have been made, but word to vec or those kind of embeddings is not created yet. So which means that I might not be sure whether the model is really great at its performance. Let's see its performance. It's evident, right? So it is kind of stagnant at 85%. Even though the training accuracy reach 100%, the validation is kind of stagnant at 80%. So which means that like the model is 85% accurate, not 100%. It's kind of overfitting. Obviously, like as I told you, like it is kind of maintaining sequential data, and many words will be common across both the both the sentiments. Let's say either 0 or 1. In that case, the model tends to overfit little quite soon. And that's why, the validation accuracy is kind of, so that's where even in transformer, because of this overfitting problem, they kind of went to a normalization, part. Without normalization, the model might not stood up correctly. Okay. So this is how you can do a sentiment analysis with the given data. Do we have any doubts or clarification at this point? Okay, that's good. Now I will challenge you. Okay, so your work is now to create, tamper this data. Okay, tamper this data and try to utilize Spacey or any pre-processing tool to pre-process the data a little better. And then you try to train with the same network and see you will be having a drastic improvement with the data, obviously. But but the problem is like when you go with trillions and trillions of word, pre-processing will become will not give a huge impact at all, because of the fact like every word might have to be contributed at some point in time, because I cannot never use stop words every time. Sometimes, when you have larger number of words, the model will become more generalized. But in this case, it's just 30,000 words. All the words wouldn't have been, appeared more than 10 times, which means that there's a high possibility the model might not converge really soon, and it will look for only the non-lexical words like this on, and, for, in, to. So that's why when you have a lot smaller data, and when you're going to use LSTM models or something like this, then do pre-processing and remove all the stop words and see whether the model works better or not. If not, then we have to go with different strategies. Okay, this is one way of training your model with LSTMs or your sequential networks. Is this clear? Any doubts or clarification at this point? uh, with that, if there are no doubts or clarification, I'll just show you one more program where I kind of utilize the same LSTM to create a new story. Okay, so what I did is like I kind of utilized a novel, a Sherlock book, a Sherlock Holmes book. I've taken that particular book as a form of a text file. I utilized the text file and learned its every words, and I tried to generate my own letters. But before we even talk about this, I will do one thing. I'll just run it. Okay, I'm gonna run. Okay, wait a minute. How many epochs I've given here? I'm gonna go with 20 epochs here. Okay, let me run it. The reason why I run it is like no, this particular data set is very big. Okay, I'm gonna just have to manage the session now. Okay. Now let's say like I will be having a very big book. Okay, Sherlock Holmes entire book have been converted into text file, so which means that it roughly has like a lack of words. Okay, so the concept which I'm trying to do here is, let's say like you have some content, like say the Sherlock Holmes comes to a hotel, deceives the the waiter, something like that. In this case, what I'm trying to do is I'm going to take the first I guess like first 20 characters. Okay, I'm going to take the first 20 characters, and I'm going to try to predict the 21st character. It's not on a word level, it's on a character level. Okay, so I'm going to take the 20 character, and I'm going to predict the 21st character. I'm going to generate the 21st character. Now I'm going to take the next 20 characters. Like I'll leave this T, and I'll take this 20 character against also there's one more character which I predicted right now. I'm going to add that, and I'm going to predict the 22nd character. Likewise, I'm going to generate contents on a character level, not on a word level, but on a character level. Okay, it sounds interesting. Yes, you can also do it on a word level. That's going to be your your work. You can also try it out. Basically, you have to predict the words against each other. So this is how once you utilize the same ideology is can be applied with an attention mechanism. That's your transformers. In that case, transformer will will bring you even more better result, because of the fact like it's attention mechanism make it really works. So what I did is like I kind of loaded the data. Okay, so this is where I load my data set. Okay, and since it is a text file, I've loaded it, and I've converted all the characters into lower characters, because I don't want to confuse myself with the capital letter and the small letter. I'm going to do that. I'm not going to do this. So I'm going to lower the entire content, and then I'm going to create a dictionary for character to numbers and numbers to character. For example, you can see, right? So this is the number which is given. So for for slash in, I'm going to map it as 0. For empty, I'm going to map it as 1. For exclamator, I'm going to map it as 2. This quotation 3. This and as 4. Likewise, for every character which I see, like all the ASCII characters. What are the ASCII characters? You can see here, right? So the text is taken from this thing, and I use a set function, which means that every character which I see here is very unique here. Okay, I'm going to load it out. Okay, so this is the entire character, which is very unique in nature. Okay, so all the characters are there, which means like comma, apostrophe, exclamatory, question mark, all the non-lexical words, non-lexical characters, all the lexical character will be there, and unique characters is found using the set function. And then I'm going to create a dictionary where I'm going to map a number to it. Usually we know that like we're going to map a number to a word, but in this case, I'm mapping a number to my characters. Similarly, for number to character, I'm just having a vice versa of it. Okay. So I've done that, and I've given a sequence length as 40, which means that 40 character will be given as input and the 41st character will be as the predictor. Okay, so that's going to be the prediction stage. So I'm using two lists here. One is the training sequence, another one is training sequence next character. This is good. This is the expected and this is the input. Okay, that is done. And then this is where I, create the sentences. Okay. I take the first 40 characters and I append in the train sequences, and I take the 41st character and I append in this particular list. So now the input and output is kind of generated. Okay. I read the entire novel, entire text file of this Sherlock Holmes book, and I've appended 40 characters here and the 41st character in the as a part of output. So you can see it has like 50,260 items, which means like, entirely it has 50,000 words. It is also having 50,260 words. Okay. So because I'm going 41st character, and then I'll take the 42nd character to plus 40. Likewise, I go step by step. Totally, I have like, 50,000 entries with me. So the entire data set contains 50,000 entries, which is a huge thing, I would say, correct? So after that, I'm just converting the letter to numbers, whatever, mapping which we have done here, right? So all the letters have been taken from this training sequence and the training sequence next character, and it has been converted into numbers. So now my feature extraction is done. And note that there's no feature extraction done here. I'm just converting my numbers or the characters into just numbers. That's all. And then this is where I generate the block. So I kind of created a block where I can able to, run this particular function after the end of each and every epoch. That is what we called as callbacks, because this is a generative model. Okay, where the model will evolve, step by step. There is no concrete evidence or there is no feedback given to the model at all, because the only feedback which the model can get is this one, the 40 characters and the 41st one. So, but but as a reader, you need to see like how the model is, forming the words. So in that case, I just generated it every epoch. The words will be generated, and we'll be the one, where you can give a pass. So what it is like, I'm going to generate 1,000 characters right now. Okay, so 1,000 characters will be generated by this network. So I'll be like, take a random seed like this when you have eliminated the impossible. So this is the random seed which I've given to the model. Okay, I can change this seed whatever I want. So from this model, a new text will be created. One character will be created. And then from that one character, I'm going to like append, I'm going to remove this W and take this entire guy, and I'll be, taking the second character output. Likewise, I'm going to, create 1,000 characters. Okay, so I'm going to create 1,000 characters, and let's say all the index and characters have been like, appended in this new text itself. Okay, simply put, I take the data, I get the probability. If the probability is above 9, probability is above 9, I'll be taking that as a probability, because I will be having a lot of probable words, right? Because the output vocab set is totally bigger, A, B, A to Z, and we have a lot of functions and other things. So if the probability is very high, only I'll be taking that as a predictor letter probability. I'll get the next index, I'll go for the next character. Likewise, slowly I'll go step by step. I'll be generating 1,000 characters. But this is just a function which will be invoked during the epoch process, but during the training process. And this is where my model network comes in play. So this is a very small model. I have 2 LSTM blocks, okay? Not one blocks, 2 LSTM layers. Each and every LSTM layers have 64 LSTM blocks inside it, okay? So basically it has 2 LSTM blocks followed by a softmax, that's all. And I want to compile the model. Oops, my bad. It has not started its training. Gosh, I should have import TensorFlow as TF. This was the culprit. Now I have to run this guy. Now you can see I'm just compiling the model. I'm giving a batches of 128 and going with 20 epochs. And note down here, I call this callback here. Okay, callback is equal to, lambda callback. On epoch n, at the end of every epoch, I'm going to call this function. What is this function? This is the generate new text function. So basically, I take the model which has been trained, and I'm going to generate 1,000 characters. Likewise, at every end of epoch, I'm going to generate some contents to see like how the model is evolving, right? So that's what we are doing here. Let's see. Obviously, it will take some, because at the end of the epoch, this callback will happen. So it has to generate, it has to infer like 1,000 times to get 1,000 characters that will be appended against it. So this will take definitely, some time to do. But I'm just basically trying to form, I'm basically trying to form a small book out of the same Sherlock Holmes. But yeah, this has become even more when I use the, transformer network. Here I just use LSTMs, but if I use transformers, the results will be even more fruitful in nature. Okay. So it might take some time. That's why I was, explaining it and running it before. But surprisingly, yeah, you can see that this is how the predictions were. This is the first 1,000 characters which has been generated by the model. You can see it's totally gibberish, correct? There is no one proper word which has been formed here, because only one word known as me has formed, but nothing has formed because this is the first epoch. It is slowly starting to evolve, right? So it will take some time. So when it reaches like some 100, I did train it for like some 150 epochs, and the results were really great. It was a very legitimate 1,000 character sentence that was really looking like a novel actually. So even though the context was not there, but the words were very clean and very effective. But since it's a character level thing, it might not have very good greater context. But when you go with the word level, obviously you'll be even getting a better results, better storyline, I would say. And again, you can see, right, it's taking more time to predict, do that. And let's see the second epoch's output. Again, some words, her, I can see one good word have been formed, and has is there to do. Somehow it is trying to form it. Likewise, it is when it goes epoch by epoch by epoch, this will basically evolves better and better and better. Okay, so this is how a generation will work, but basically the concepts are the same. Okay, so whatever thing which I've done is the same. The only thing is, like, if you want to use transformer, you can use transformers. That's all. Transformer, obviously transformer will not evolve at this point, because you have very less data. It's just 50,000 characters. 50,000 sentence or 50,000 and a mark is very less. For a transformer to work, we need at least some lakhs and lakhs of data for it to evolve a little better. Without that, the model will not be evolving really great. So that's one more thing which you want to keep in. So if you want to have lakhs and lakhs of data, you should be having a very bigger, a GPU reserve to do that. Yeah, the third epoch is also done, surprisingly. Okay, now you can see like this was and has, we, man, the, I, they, there. So likewise, it is slowly, it's like a baby trying to, learn forming the words. But you can see the 3-letter words are being formed very clearly right now. Sit is formed correctly, the is formed correctly, is formed correctly, met any, this is also formed correctly, but there's no space in between. And hit, I could say like, some words, hat, mat. That's good to see, right? So if it goes epoch by epoch by epoch, it gains a great. So now we can see the accuracy is very less. The prediction accuracy is very, very less in the main training, and the generation is that's why it's like this. If the accuracy slowly, the accuracy will shoot up. You can see that the first epoch accuracy is like 29. Second epoch is 32. The fourth one is 35. And the fifth one is like slowly increasing. This is the fourth ones. So likewise, you can able to form a very neat word when you're training for like more than 100 epochs or something like that. Okay, but this is one way of doing it. But do explore it. Use the word instead of characters. Use a different architecture like transformers or attention networks or something like that. That way you can evolve. But this is the basic essence of how do you handle NLP. That's all. Very simple. This is how GPT is also formed, but GPT is like a higher scale network. We have a bigger transformer architecture and we have a large pool of data to deal with. That's all. That's the basic. This is a small scale of doing things because we don't have the liberty of having a very big GPU to train. So this is the maximum which we can do at the current stage. So do we have any doubts or clarification at this point? Okay, that's great. If there are no doubts or clarification, stay tuned for the next session. But before you go, if you have any doubts or clarification, regarding like how to, download materials, the presentations or these videos from the portal, just to ping here. Okay, so I guess either Amar or Triru will be like, giving you the query. So they will give you some insight about like how to do that. Now you can utilize this time to understand about how this dashboard thing works and how do you download stuffs. And yeah, one more info, like tomorrow, we'll be like going into, more deeper into GPT models, how they have evolved, and how do you know how to prompt it correctly? What kind of prompts you can use to, to effectively utilize the model or its, or its capabilities. We can, talk about that. You can also come up with some interesting queries, try do some homework, see like what kind of queries make the model confused. You can do all these kind of things. Let's see. Thank you for the time. We'll meet again tomorrow, but please do stay for, to get clarified about the portal issues like downloading stuffs and things like that. Thank you.
Yeah, thank you, Deep. Guys, if you have a query or a question, please drop in the chat box. I will take it up. Yeah, Kiruna has already posted the email ID in the chat box. If you have any query or question, please share on email as well, edl@excelr.com. Guys, anything? You are asking the questions between the sessions, like regarding to the LMS certificate next session. So now you can ask. I think no one has have any query or question. There is one question from Sachin. Sir, when will give the assignment? So you will get the assignment by Monday or Tuesday, and you will get in the LMS. Okay. Yes. So tomorrow is the last session of our program, day 15. Sachin, no need to submit. It's just for your practice purpose. Yeah, you're welcome. So that Fatima is asking, will get certificate by Monday. So guys, it will take 7 to 8 working days. So we'll explain these things in tomorrow's session very clearly. Fatima, clear? Oh yes, Devnath, you can. Tirunat, I think there is no any query question, so you can wind up.